Hey everybody. Today we're doing limits involving trig functions. Mostly we're going to be interested in indeterminate forms here, but I also first want to run through a few very useful and important facts that'll help us solve a lot of problems in Calculus 1. First of all trig functions have the direct substitution property. That means if you have a value x equals c in the domain of the trig function, you can do a limit at x equals c just by plugging in. For instance, the limit as x goes to pi of cosine of x is going to be the cosine of pi, otherwise known as -1. Here, as usual, I'm working in radians. The limit as theta goes to 0 of 3 tangent theta is 3 times the tangent of 0, or 0. All trig functions are periodic. They never settle down to any single value as x goes to positive or negative infinity. So they have no limit at positive or negative infinity. To say that slightly differently, no trig function has a graph with a horizontal asymptote. Some trig functions do have vertical asymptotes, however. For instance, secant of x is equal to 1 over cosine of x, and so it's going to have a vertical asymptote whenever cosine of x is equal to 0. At those values, the denominator will be 0 and the numerator will not be. That occurs when x is negative pi over 2, 3 pi over 2, and so on. We can do one-sided limits at values like this. For instance, the limit as x goes to pi over 2 from the right of secant of x, trying to get a little bit more information about what's happening at this vertical asymptote. We rewrite secant of x as 1 over cosine of x. Clearly the denominator is going to 0, but the numerator is not here. We'd like to know whether this function is going to positive infinity or negative infinity by looking at the sign of cosine of x. Here x is a little bit bigger than pi over 2, so x is going to be in the second quadrant when we view it as an angle. That means the cosine is going to be negative, and therefore this fraction 1 over cosine of x has to be going to negative infinity. We can verify this visually by looking at the graph of y equals secant of x. Here I've drawn that graph, and I've also labeled the asymptote at x equals pi over 2. You can see that as x gets closer and closer to pi over 2 from the right, this function is going downwards. It's going towards negative infinity. The hardest and probably most important trig limits in a Calc 1 class involve 0 over 0 indeterminates. That is, fractions where both the numerator and denominator are going to 0. Problems like that are almost always solved using these two facts. First, the limit as x goes to 0 of sine of x over x is 1. Second, the limit as x goes to 0 of cosine of x minus 1 over x is 0. Let's do a few problems using these identities. Number 1. Limit as theta goes to 0, the sine of 4 theta over 3 theta. So right away, I see that I'm going to want to use that first fact there on the upper left. However, I have one small problem. The inside of the sine function here is 4 theta, but the denominator is 3 theta. They're not exactly the same, and I can only apply that identity, limit as x goes to 0, sine x over x equals 1, if the inside of the sine function and the denominator are the same. So my strategy is just going to be one of wishful thinking. I'm going to rewrite this fraction as the fraction that I actually want, the one that I actually know how to evaluate the limit of, sine of 4 theta over 4 theta. And then I'm just going to multiply by a constant that makes that equal sign actually true. So if I want a denominator of 4 theta instead of 3 theta, I have to multiply by 4/3. Now the 4/3 can be factored out of the limit, and I can evaluate this limit using that fact on the upper left. That limit is going to be 1, so the overall limit, the answer to this problem, is 4/3. Example 2. The limit as t goes to 0, cosine t minus 1 over sine of t. Notice that both the numerator and denominator are going to 0 here. We have an indeterminate form. We have to do a little bit of work before we can evaluate this limit. Here, the idea is going to be to split up this fraction into two pieces, where the first one looks like one of the identities and the second one looks like the other. So I'll take the cosine t minus 1 and divide by t, so that now I have something looking like the identity on the upper right, and multiply by t over sine of t, which now looks like the reciprocal of the identity on the upper left. The first of these limits is going to go to 0, the second one is going to go to 1. Since each of these two limits is going to exist, I can break up the limit of the product as the product of the limits, and then evaluate the limits separately. In this case, I just get 0. One more example. Limit as x goes to 0, x times tangent of x over sine 4x times the sine of 5x. So here again, if I try plugging in, I get 0 over 0. This is an indeterminate form. I'm going to want to rewrite this fraction in a form where I can apply those two identities from the previous slide. In particular, I know I'm going to have to take out the tangent of x and rewrite it as a sine of x over cosine of x. First, let's break up this product into two pieces. X over the sine of 4x times the tangent x over sine 5x. My idea is that first factor, x over the sine of 4x, can be evaluated much as example 1 was. I'm going to rewrite it as 4x over sine x times 1/4. So multiplying the top by 4 so that I get the form that I need, and then dividing by 4 so that the equal sign is actually true. While I'm at it, I'm going to rewrite tangent of x as sine x over cosine of x. So now let's think about that second factor, sine x over cosine x times sine x times sine x of 5x. The 1 over cosine of x, I'm not worried about. That is going to be able to is something I can evaluate using direct substitution because the cosine of 0 is 1. I'm thinking about the sine x over sine of 5x. I'm going to break that up into two fractions, sine x over x and 5x over sine of 5x, because each of those limits can be evaluated using the first of the identities from the previous slide. Here I've multiplied the numerator by 5, so to keep things equal, I'm going to be multiplying by 1/5 as well. Now each of these factors has a limit that I can evaluate. In particular, each of the limit exists, so I can do the limits separately. I get 1 times 1/4 times 1 times 1 times 1 times 1/5. Overall, I'm getting 1/20.